In 1995, the director of the most important telescope in history was told he would lose his job if he pointed it at a patch of sky where there was nothing. He did it anyway. In 2023, an astronomer in Melbourne ran a software pipeline on a pinprick of infrared light, and the two numbers it returned were so wrong, he thought the instrument was broken. It was not broken. And right now, sitting in the data archives of the James Webb Space Telescope, there are 340 objects that do not appear in any simulation, any prediction, or any theoretical framework written before 2022. Nobody knows what they are. 3 stories, 3 decades, 3 different telescopes. They do not look connected, but they are the same story. And the thing that connects them, the thread running through a grain of sand in 1995 to the spectral data on a screen in Pisa in 2024 to a 5 sigma disagreement that has no solution, is a single question that the standard model of the universe cannot answer. Not because the answer is hard, because the answer breaks the model. Tonight, we are walking through 23 years of deep field observations, from Robert Williams betting his career on nothing, through the 6 galaxies that earned the name universe breakers, to an oxygen emission line detected by armor in a galaxy that should not exist, and finally to a tension in the expansion rate of the universe that was supposed to go away and instead got worse. By the end, you will understand why the story you were told about the cosmos, its age, its composition, its fate, may be built on a framework that has been failing the same test in the same direction for longer than most of you have been alive. So settle in, get comfortable, subscribe if you have not already, and if you want more of this, deeper dives across physics, cosmology, and the things the textbooks leave out, the Patreon is where that lives. Stay for this one. The pattern at the center of it is something I still do not know how to sit with comfortably. Let's start where it started. In 1995, a man bet his career on a patch of nothing. Not a star, not a nebula, not a known galaxy. Nothing. A tiny square of sky in the constellation Ursa Major that every survey, every catalogue, every instrument on Earth said was empty. Robert Williams, the director of the Space Telescope Science Institute, pointed the most expensive scientific instrument in human history at that nothing and held the shutter open for 10 consecutive days, 100 hours of exposure time on the Hubble Space Telescope, aimed at a region of sky so small you could cover it with a single grain of sand held at the end of your outstretched arm. His colleagues told him he was wasting irreplaceable observing time. His advisory committee refused to endorse it. Some of them warned him, privately and not so privately, that it could be a career-ending embarrassment, the kind of public failure that would make NASA reconsider whether the telescope even needed a director at all. Williams did it anyway. He told them that if it failed, he would resign. And when the image came back, when the data finished processing, and the first full composite was assembled on a monitor in Baltimore, what was in that patch of nothing was not nothing. It was 3,000 galaxies. Not stars, galaxies. Entire island universes, each one containing hundreds of billions of stars, packed into a keyhole of sky that covers 1/24 millionth of the visible heavens. Some of them were so distant, their light had been traveling for over 12 billion years, meaning they existed when the universe itself was still in its infancy. They had been there the whole time, behind every dark gap in the night sky. In every direction, there were galaxies. Not dozens, not hundreds. Thousands, and nobody knew. And here is the part that never makes it into the popular version of this story. The part that matters now, 23 years later, more than it did when Williams first saw the image on his monitor. The Hubble Deep Field was not just a census. It was not just a prettier version of what we already suspected. It was a test, an unintentional, accidental, devastating test of the model that describes how the universe works. Because if the model was correct, if Lambda CDM, the standard cosmological model, accurately described how galaxies formed and grew in the early universe, then it should have predicted roughly how many galaxies Williams would find in that grain of sand, and roughly what those galaxies would look like, and roughly how old they would appear. The model did make those predictions. And it was wrong. Not catastrophically wrong. Not in 1995, but wrong in a specific direction. There were more galaxies than the model expected. They were slightly more luminous. They appeared slightly more structured. The discrepancy was small enough that it could be absorbed into the error bars. It could be attributed to statistical fluctuations. It could be explained away by tweaking the parameters, and it was. But the direction of the error, the fact that reality contained more than the model predicted, rather than less, that direction turned out to be a signal that would get louder with every passing decade, with every deeper observation, until it became a scream that could no longer be ignored. That image, called the Hubble Deep Field, became one of the most important photographs ever taken. It should have been the end of the story. We pointed the telescope at nothing. We found everything. We updated the textbooks. We moved on. But that is not what happened. What happened is that astronomers kept looking. They pointed Hubble at the same kind of empty patch again in 2003, and what they found was worse. They assembled an even deeper image in 2012, and what they found was worse again. And then, in 2022, a new telescope arrived, one with a mirror nearly 3 times wider and eyes tuned to wavelengths Hubble could never see. The James Webb Space Telescope looked into that same darkness and found something that has forced physicists to use a very specific word in their published, peer-reviewed papers. A word that almost never appears in professional science. The word is impossible. Galaxies that should not exist. Structures that formed too fast, too early, too massive for any model of the universe to explain. Objects so contradictory to the predictions that one research team, publishing in Nature in 2023, gave them a name that stuck. They called them universe breakers. And the people who found them are still trying to figure out what they mean. Because every proposed solution so far has failed. Every deeper look has made the problem not better, but measurably, quantifiably worse. And a separate class of objects, hundreds of compact red points of light that nobody predicted, nobody modeled, and nobody can fully explain, has emerged from the same data like blood spots on a dark floor. I spent an unreasonable amount of time reading the papers behind this story. Not the press releases, not the summaries on YouTube or science news sites, the actual publications in Nature, in the Astrophysical Journal, in Astronomy and Astrophysics, in the monthly notices of the Royal Astronomical Society going back to 1996. And what I found in those papers is a pattern that I think deserves far more attention than it has received. Every time we build a better telescope and point it at the deep universe, it does not confirm what we expected. It contradicts it. Every single time. For 23 consecutive years, the data has been telling us something. And the response from the institutions that are supposed to interpret that data has been, consistently and systematically, to patch the models, adjust the parameters, and quietly hope the next data set is less embarrassing. It has not been less embarrassing. It has been more embarrassing. Every single time. And the most recent data from JWST in 2024 and 25 and into 26 is not just embarrassing. It is, by the published standards of the people who collected it, physically impossible under the current model of the universe. That model has a name. It is called Lambda CDM, which stands for Lambda Cold Dark Matter. It is the standard model of cosmology. It has been the reigning framework for how the universe works for over 2 decades. It tells you the universe is 13.8 billion years old. It tells you the universe is made of roughly 5% ordinary matter, 25% dark matter, and 70% dark energy. It tells you the universe began with a big bang, expanded, cooled, and gradually assembled stars and galaxies through a slow, hierarchical process of gravitational collapse. It is the foundation for nearly everything you have ever read about the cosmos. And the data from one patch of sky stared at for 23 years is pulling it apart at the seams. This is not fringe science. This is not speculation. This is published, peer-reviewed physics appearing in the most prestigious journals on Earth. And the fact that you probably have not heard the full scope of what has been found should, I think, genuinely make you angry. Let me take you back to the beginning. Because the beginning is a story about a man who risked everything to look at nothing. And what that nothing contained was the first crack in the foundation of modern cosmology. Robert Williams was born on October 14th, 1940. He grew up in the United States, got his bachelor's degree from the University of California at Berkeley in 1962, and his doctorate from the University of Wisconsin. He spent 18 years as a professor of astronomy at the University of Arizona, a long, productive, unremarkable career by the standards of his field. Then, in 1986, he moved to Chile to run the Cerro Tololo Inter-American Observatory, a major optical observatory in the Chilean Andes, and he directed it for 7 years. By the time he was appointed director of the Space Telescope Science Institute in 1993, the institution that manages the scientific operations of the Hubble Space Telescope, Williams was 53 years old. He was well established, well respected, a member of the American Academy of Arts and Sciences, and entering what, by all reasonable expectations, should have been the quiet, honorable, final act of a distinguished career. He had nothing left to prove and nothing obvious left to risk. That last part turned out to be important because what he did next was the kind of decision that only someone with nothing left to lose would make, and that most of the people around him were too careful, too career conscious, and too invested in the existing system to even consider. As director of STSCI, Williams had a privilege that came with the job. 10% of the Hubble Space Telescope's total observing time was designated as director's discretionary time. This was a holdover from the ground-based observatory tradition, where the director of a major facility had the authority to allocate a fraction of observing time without going through the standard peer review process. In practice, at STSCI, previous directors had used this time carefully. Small projects, follow-up observations, safe, defensible uses that nobody could object to. The reason they played it safe was that Hubble's time was the most valuable commodity in astronomy. For every hour the telescope spent observing one target, 100 other proposals went unfunded. Researchers with years of work riding on a few dozen orbits of Hubble time watched their proposals get rejected because there was not enough time for everyone. The idea that a director would take a large chunk of that time and spend it on something speculative, something that might produce nothing at all, was not just unconventional. It was, in the culture of that institution, something close to irresponsible. Williams wanted to point Hubble at a part of the sky where there was nothing to see, and not just for a few hours, for 10 days. The logic behind the idea was deceptively simple but genuinely radical. Every deep observation Hubble had made up to that point had targeted something specific: a known galaxy, a star-forming region, a gravitational lens, something astronomers already had reason to believe was interesting. Williams wanted to know what would happen if you did not aim at anything, if you just picked a random, empty direction, a patch of sky with no catalogued objects at all, and stared at it for as long as the telescope's schedule would allow. What would emerge from the blackness between the stars? The existing models and surveys predicted. The answer was probably not much. A scattering of faint, distant galaxies, maybe a few dozen, certainly nothing that would justify burning 150 orbits of irreplaceable Hubble time. Williams brought the proposal to his scientific advisory committee. The reaction was hostile, not skeptical, hostile. These were accomplished astronomers, people with their own programs, their own data needs, their own graduate students waiting for observations. And the director was telling them he wanted to take 10% of the telescope for 10 days and aim it at nothing. The committee did not just decline to endorse the observation. Several members told Williams directly that if the image came back empty, if this turned out to be nothing more than an expensive photograph of darkness, the consequences would be severe, not just for him personally, for the telescope, for the program, for the public perception of NASA's science portfolio. And the context makes that fear understandable, because Hubble had already survived one near-death experience. In 1990, when the telescope was first deployed and astronomers pointed it at a star to check the focus, the images came back blurry. The primary mirror, 2.4 meters of precisely ground glass that was supposed to be the most perfect optical surface ever created, had a flaw, a manufacturing error called spherical aberration, caused by a mistake in the testing equipment used to shape the mirror. The mirror was ground to the wrong specification. It was off by about 2 microns, roughly 1/50th the width of a human hair, which does not sound like much until you realize that at those scales of precision, 2 microns is the difference between the sharpest telescope in existence and a $2.2 billion piece of nearsighted junk. The public humiliation was enormous. Late-night comedians made jokes about it. Congressmen questioned the competence of NASA. The spherical aberration scandal became shorthand for government waste and bureaucratic failure. It took 3 years and a high-risk servicing mission by space shuttle astronauts in December 1993 to install corrective optics, tiny mirrors shaped to cancel out the primary mirror's defect. That restored Hubble to full capability. By 1995, Hubble was producing beautiful, sharp images and doing spectacular science. But the memory of that humiliation was still raw. The institution was still recovering its credibility. And now, the director wanted to gamble 150 orbits on a long shot. Williams listened to every objection. He understood the risk, and then he said something that I think reveals more about how science actually works, about the real dynamics of discovery and institutional inertia than anything you will read in a textbook. He told them, and this is his direct quote to National Geographic, "Scientific discovery requires risk." And I was at a point in my career where I said, if it is that bad, I will resign. I will fall on my sword. In another interview, he put it even more bluntly. It took me promising to turn in my resignation to convince them. The director of the most important telescope in history had to threaten to end his own career in order to be allowed to do science with it. Not because the idea was bad, not because the method was unsound, but because the culture of the institution valued predictable, incremental progress over the kind of risky, open-ended observation that might actually discover something nobody expected. That dynamic, the systemic preference for confirming what we already think we know over discovering what we do not, is going to repeat itself throughout this entire story. It is the background radiation of this narrative. Remember it. Williams chose his target with care. He needed a patch of sky in Hubble's continuous viewing zone, a region near the North Celestial Pole where the telescope can observe without the Earth blocking its line of sight on every 96-minute orbit. The patch had to be free of bright foreground stars whose optical halos would contaminate the image, and it had to be genuinely empty. No known galaxies, no catalogued objects of any kind. He settled on a region near the handle of the Big Dipper in Ursa Major. The field measured 2.6 arc-minutes. On a side, to understand how small that is, I need you to do something. Hold your arm out in front of you, as far as it will go. Now hold up a single grain of sand between your thumb and your finger. The area of sky behind that grain of sand is roughly the size of the Hubble Deep Field, 1/24 millionth of the entire sky. That is what Williams was betting his career on. Between December 18th and December 28th, 1995, Hubble took 342 separate exposures of that grain of sand, using its wide field and planetary camera too. The exposures were taken through 4 different color filters, building up signal in ultraviolet, blue, red, and near-infrared light. The individual frames were stacked, aligned, and combined, a painstaking process that took weeks, gradually coaxing signal out of sources so faint that no single exposure could detect them. Cosmic ray hits had to be removed. Satellite trails had to be masked. The background had to be modeled and subtracted. When the final composite image was assembled in January of 1996, what it showed was not what anyone expected. It was not within the range of what anyone had seriously predicted. The image contained approximately 3,000 galaxies. Not stars, galaxies, entire island universes, ranging from large, clearly resolved spirals and ellipticals in the relative foreground to tiny, irregular, barely visible smudges at the very limit of detection that turned out to be among the most distant objects ever observed. Some of those faint smudges were galaxies as they existed more than 12 billion years ago, when the universe was not even 1 billion years old. They were among the youngest galaxies ever seen, caught in the act of assembling themselves from the primordial gas, and they were everywhere, in every direction, at every distance. The supposedly empty sky was full. I want to make sure you feel the weight of what that means, because the number 3,000 in a tiny patch can sound abstract. Let me make it concrete. If a random, undistinguished patch of sky this small contains 3,000 galaxies, and if the rest of the sky is statistically similar, which subsequent observations confirmed it is, then the total number of galaxies in the observable universe is not in the billions, it is in the hundreds of billions. A 2016 study led by Christopher Consellis at the University of Nottingham, published in the Astrophysical Journal, used the deep field data combined with mathematical models of galaxy populations at higher redshifts to estimate the total number of galaxies in the observable universe. Their result was approximately 2 trillion, 2,000 billion galaxies, each containing billions to hundreds of billions of stars. And the first hint of that number came from staring at 1 grain of sand for 10 days. The universe, it turned out, was not just bigger than we thought. It was orders of magnitude more populated. And we found out because one man threatened to resign if his colleagues would not let him look at nothing. Williams presented the Hubble Deep Field results at the January 1996 meeting of the American Astronomical Society. The room went quiet. The committee members who had opposed the observation were forced to acknowledge that the HDF was not just a success, but one of the most consequential observations in the entire history of astronomy. Williams would receive the Beatrice M. Tinsley Prize in 1998, the NASA Distinguished Public Service Medal in 1999, and the Karl Schwarzschild Medal in 2016 for this work. He later became president of the International Astronomical Union. The man who had to threaten his own resignation in order to look at nothing had fundamentally and irreversibly changed our understanding of the universe. And there is something else Williams did during his tenure at STSCI that deserves mention, because it connects to the broader story in a way that most people do not know. In 1996, the same year he released the Hubble Deep Field, Williams made another controversial decision with his discretionary time. He offered observing time to two competing teams that were using distant Type Ia supernovae to measure the expansion rate of the universe. One team was led by Saul Perlmutter at Lawrence Berkeley National Laboratory. The other was led by Brian Schmidt and Adam Riess. Both teams were chasing the same question, whether the expansion of the universe was slowing down as everyone expected, or doing something else. Williams gave them time on Hubble. 2 years later, both teams independently announced the same result. The expansion of the universe is not slowing down. It is accelerating. Something is pushing the universe apart, a force that was given the placeholder name dark energy. That discovery, enabled in part by Williams's willingness to take risks with Hubble time, won the Nobel Prize in Physics in 2011. The man who stared at nothing was also the man who helped reveal the force that is tearing the cosmos apart. And the irony that will become clear later is that both of these discoveries, the deep field and dark energy, are now converging on the same crisis. I want to spend a moment on the scale of what the Hubble Deep Field actually revealed, because the number 3000 can sound abstract when you are talking about galaxies. Let me try to make it tangible. Imagine you are standing in a field at night, away from city lights, looking up at the sky. You can see, on a clear night, roughly 5,000 stars with the naked eye. Those are all stars in our own galaxy, the Milky Way. Now imagine holding a drinking straw up to your eye and looking through it at a random dark patch between those visible stars. The area of sky you see through that straw is much larger than the Hubble Deep Field. Williams was looking through something much, much smaller than a straw. He was looking through a grain of sand, and in that grain of sand there were 3,000 entire galaxies. Now multiply. There are roughly 24 million of those grain of sand patches needed to cover the entire sky. 24 million times 3,000 gives you about 72 billion galaxies, just from the raw count, and that is a lower bound because the faintest galaxies at the greatest distances were below even Hubble's detection limit. When Conselis and his team at Nottingham did the full statistical accounting in 2016, including corrections for the galaxies too faint to be detected, the number came back at 2 trillion, 2,000 billion galaxies, each one a gravitational island containing billions of stars, each star potentially hosting planets. And behind every dark gap in the night sky, in every direction, at every depth, they are there. The universe is not mostly empty. The universe is full. It is crowded. And we had no idea until one man threatened to resign over a grain of sand. There is a detail about the Hubble Deep Field image that rarely gets mentioned, but that I think is important for understanding what happens next. The very faintest objects in the HDF, the tiny red smudges at the extreme limit of detection, were at redshifts of approximately 4. That means their light left them roughly 12 billion years ago, when the universe was about 1.5 billion years old. Those were the most distant galaxies anyone had ever seen at the time, and they were there, at the edge of detection, whispering that there was more to find if only we could look deeper and longer and in the right wavelengths. The HDF ended not because there was nothing left to see, but because Hubble had reached the limit of what it could detect. The darkness at the faintest end of the image was not empty. It was the edge of Hubble's capability. Beyond it, there were more galaxies, more structure, more surprises. We just could not see them yet. But in 1996, the Hubble Deep Field did not look like a crisis. It looked like a triumph. And the early galaxies it revealed, those faint, distant smudges at the edge of detection, mostly looked the way the models said they should. Small, irregular, still in the process of assembling. The hierarchical model of galaxy formation, where small clumps of gas merge into larger structures over billions of years, appeared to hold. Lambda CDM was not threatened. Everything was fine. Everything was fine until they looked deeper. In 2003, Stephen Beckwith, who had succeeded Williams as director of STSEI, decided to push the gamble further. Beckwith committed an extraordinary allocation, 400 Hubble orbits, to a new deep observation. Not 150 orbits, 400. The target was a patch of sky in the southern hemisphere constellation Fornax, carefully chosen to avoid bright stars and to allow observations from both Hubble and ground-based facilities in Chile. The field was 2.4 arc-minutes on a side, roughly 1/26 millionth of the full sky. The observation ran from September 24, 2003 to January 16, 2004. 800 individual exposures, 11.3 days of cumulative exposure time, nearly 1 million seconds with the shutter open. When you hear that number, 1 million seconds, I want you to think about what it represents. That is 11.5 days of a 2.4-meter space telescope, collecting every photon it can from a patch of sky smaller than a grain of sand. Every photon from galaxies so distant and so faint that their light had been traveling for over 13 billion years. Photons that left those galaxies when the universe was a few hundred million years old, that traveled across the expanding cosmos for 95% of the age of the universe, only to end their journey on a CCD detector the size of a postage stamp orbiting a small rocky planet 340 million kilometers away. The result was called the Hubble Ultra Deep Field. When it was released to the public in 2004, it contained not 3,000 galaxies, but approximately 10,000. In an area of sky 1/26 millionth of the total, 10,000 galaxies, including objects visible as they were just 400 million years after the Big Bang. 400 million years, the universe is 13.8 billion years old. These galaxies existed when the cosmos was less than 3% of its current age. The project lead, Massimo Schiavelli, described it at the time with a phrase that sounds routine, but carries real weight when you stop to think about what it actually means. He said, "Hubble takes us to within a stone's throw of the Big Bang itself." And what those early galaxies showed was the first hint of a problem. Not a crisis, not yet, but a discomfort. There were more of them than the models predicted. They were more luminous than expected for their age. Some appeared more structured, more organized than the hierarchical models said they should be, after just a few 100 million years of assembly. The standard models could accommodate the results, but only by adjusting the parameters. Maybe star formation began a little earlier than previously assumed. Maybe the efficiency was a little higher in the first generation of galaxies. Maybe the initial mass function was different. These were reasonable adjustments, plausible, defensible, and they all went in the same direction, toward a universe that assembled faster, earlier, and more efficiently than Lambda CDM naturally predicted. Then, in 2012, a team led by Garth Illingworth at the University of California, Santa Cruz, decided to squeeze every last photon out of the data. They took every observation Hubble had ever made of the Ultra Deep Field region, over an entire decade of accumulated exposures, and combined them into one composite image. The total exposure time exceeded 2 million seconds. 23 days. 23 days of staring at one patch of sky accumulated over 10 years of observations. The result was called the Hubble Extreme Deep Field, the XDF, and it remains one of the deepest optical and near-infrared images ever taken. It contained around 5,500 galaxies, some observed as they existed just 450 million years after the Big Bang. One candidate object, designated UDFA 3, 9, 5, 4, 6, 2, 8, 4, appeared to sit at a redshift of approximately 10.3, which, if confirmed, would have made it the most distant galaxy known at that time. Illingworth said, "The XDF is the deepest image of the sky ever obtained and reveals the faintest and most distant galaxies ever seen. And those faint, distant galaxies continued the same pattern. More than expected. More luminous than expected. More structured than expected. The uncomfortable strain on Lambda CDM that had begun with the ultra-deep field was getting tighter with each passing year, each additional dataset, each deeper exposure. But the adjustments were still within the range that the model could absorb. Star formation was simply more efficient in the early universe. That was the fix. Maybe the conditions were different. Maybe the gas was more concentrated. Maybe there were processes at work in those first few 100 million years that allowed galaxies to build themselves faster than the standard parameters assumed. These were not unreasonable ideas. They were plausible extensions of existing physics. They were also, in retrospect, the first symptoms of something much larger. But in 2012, nobody could have known that. There is something else I should tell you about the XDF results that connects to the larger pattern. The galaxies at the very edge of the XDF's detection limit, the faintest, most distant objects in the image, showed hints of something that troubled a small number of theorists, but that most of the community was content to set aside for later analysis. A few of those galaxies appeared to have rest frame ultraviolet luminosities that were higher than expected for their inferred masses. In other words, they seemed too bright, not impossibly bright, not crisis-level bright, but brighter than the standard models predicted for galaxies at that age and mass. There were various ways to explain this. Maybe the star formation rates were being overestimated from the UV luminosity. Maybe the stellar populations included a higher fraction of hot, young, massive stars than the models assumed. Maybe there was a contribution from an active galactic nucleus that was boosting the UV emission. Each of these explanations was reasonable. Each could absorb the discrepancy. And so the community absorbed it, adjusted the parameters, and moved on. But there was a theorist who did not move on. Michael Boylan-Kolchin, then at the University of Maryland before moving to the University of Texas at Austin, was keeping a quiet, running tally of these adjustments. Every time a new deep observation found slightly more galaxies, or slightly brighter galaxies, or slightly more massive galaxies than Lambda CDM predicted at high redshift, the community adjusted and continued. Each individual adjustment was small. Each was defensible. But Boylan-Kolchin noticed that they always went in the same direction. More structure, earlier, more efficiently. That is not what random errors look like. Random errors scatter in both directions. A systematic offset that always points the same way is not noise. It is a signal. He did not publish this concern in 2012. There was not enough data to make a compelling case. But he was watching. And when JWST delivered its first results a decade later, Boylan-Kolchin was already prepared to do the calculation that would quantify just how far outside the bounds of Lambda CDM the new data had gone. He had been waiting for the instrument that would turn a whisper into a shout. I want to pause here and make sure something is visible about this sequence, because the pattern matters more than any individual data point. 1995, 2003, 2012, 3 observations, 3 different directors, 3 different instruments and filter sets, 3 different patches of sky in Ursa Major and Fornax and the XDF subset. 3 different decades. And every single time, the same result. More than expected. Each time the models had to be revised, and each time the revision went in the same direction, toward a universe that built itself faster earlier and more efficiently than Lambda CDM naturally allows. That is a trend line. And a trend line that points the same direction across 3 decades of independent observations, using different instruments, different analysis pipelines, different research teams, is not a series of flukes. It is a signal, and it was pointing very clearly and very consistently toward a conclusion that nobody in the field wanted to follow to its logical end. Because the logical end was not that Lambda CDM needed adjusting. It was that Lambda CDM was wrong about the early universe in a fundamental way. And if it was wrong about the early universe, then everything built on top of that foundation, every measurement of dark matter density, every prediction about dark energy, every confident statement about the age and fate of the cosmos would have to be reconsidered. But in 2012, the telescope that would turn a trend into a crisis was still sitting in a clean room at the Goddard Space Flight Center, more than a decade behind schedule and more than $4 billion over its original budget, being painstakingly assembled, mirror segment by mirror segment, in the most ambitious and most expensive scientific instrument ever constructed by the human species. Its name was the James Webb Space Telescope. And what it would find, in the same darkness that Williams had stared into 30 years earlier, would not just continue the pattern, it would break the ceiling. The journey from clean room to operational observatory was itself a story of risk and institutional endurance that mirrors the Williams decision in its own way. JWST was originally conceived in 1996, 1 year after the Hubble Deep Field, with an estimated budget of $1 billion and a planned launch date of 2007. By the time it actually launched on December 25, 2021, the budget had grown to approximately $10 billion, and the schedule had slipped by 15 years. There were multiple near cancellations. In 2011, the U.S. House Appropriations Committee voted to defund the telescope entirely, citing cost overruns and schedule delays. The project was saved by a bipartisan coalition in the Senate, but the political scars ran deep. Every year of delay, every $1 billion added to the budget increased the pressure on the telescope to deliver results that would justify the investment. The irony is that the results it delivered did justify the investment beyond any reasonable expectation, but not in the way anyone had planned. JWST was supposed to confirm the story of the early universe. Instead, it rewrote it. The 344 single-point failure mechanisms in the deployment sequence were not an exaggeration for dramatic effect. That was the actual engineering assessment. JWST could not be serviced. Unlike Hubble, which orbits Earth at 547 kilometers and was visited by space shuttle crews 5 times for repairs and upgrades, JWST orbits the Sun at the L 2.1.5 million kilometers from Earth. No crewed spacecraft has ever traveled to L2. If any of those 344 mechanisms failed, the telescope would be, at best, partially functional, and at worst, a $10 billion piece of space debris. The primary mirror had to unfold from its stowed launch configuration, with each of the 18 hexagonal beryllium segments deploying and then being aligned to a precision of about 150 nanometers, roughly 1,000th the width of a human hair. The 5-layer sunshield, each layer thinner than a human hair and made of Kapton polyimide, had to separate, tension, and hold its shape despite operating in a vacuum at temperatures ranging from 350 kelvins on the sun-facing side to 40 kelvins on the instrument side. Every latching mechanism, every motor, every cable, every deployment step had to work perfectly in sequence, with no option for a do-over. And they did, all 344 of them, over the course of 29 days, while astronomers around the world watched telemetry data with a mixture of hope and barely suppressed terror. Every mechanism fired, every motor turned, every latch released. When the final mirror segment clicked into alignment and the first calibration images came through, the resolution was not just acceptable, it was perfect. Better than specification. The 18 separate mirror segments were functioning as a single, seamless 6.5-meter mirror, producing images sharper than anything in the history of optical or infrared astronomy. The relief in the community was palpable, but it was quickly replaced by a different kind of tension, because now the telescope was working, and that meant the data was coming, and the data was about to upend a generation of assumptions about the early universe. JWST launched on Christmas Day 2021 aboard an Ariane 5 rocket from the European Space Agency's facility in Kourou, French Guiana. The launch was watched by millions, and the tension was real because there were 344 single-point failure mechanisms in the deployment sequence. 344 things that had to go right, in order, with no possibility of repair, on an instrument that cost approximately $10 billion to build and that would operate 1.5 million kilometers from Earth, far beyond the reach of any servicing mission. Every mirror segment had to unfold. Every sunshield layer had to separate in tension. Every actuator had to work. And they did. All of them. The telescope reached the second Lagrange point, a gravitationally stable orbit, where it could keep its 5-layer sunshield pointed at the Sun, Earth, and Moon simultaneously, while its mirrors and instruments cooled to operating temperatures around 40 kelvins, or -233 degrees Celsius. Cold enough that the telescope's own infrared glow would not drown out the faint signals from the distant universe. The key difference between JWST and Hubble is not just the size of the mirror, although that matters. Hubble's primary mirror is 2.4 meters across, giving it a collecting area of about 4.5 square meters. JWST's primary mirror, assembled from 18 hexagonal gold-coated beryllium segments, is 6.5 meters across, with a collecting area of approximately 25 square meters, 6.25 times larger. More collecting area means more photons, which means you can see fainter objects in less time. But the critical difference is the wavelength range. Hubble sees primarily in ultraviolet and visible light, with some near-infrared capability out to about 2.5 microns. JWST sees in infrared from 0.6 to 28.5 microns. And this matters for one very specific reason that is absolutely central to everything that follows. Light traveling across the expanding universe gets stretched. The fabric of space-time itself is expanding. And as it does, the wavelength of every photon traveling through it increases. This is called cosmological redshift. Blue light becomes red light. Red light becomes infrared. Ultraviolet light from the very first stars and galaxies emitted 13 billion years ago arrives at Earth as mid-infrared. Hubble could not see it. Those wavelengths were below its detection threshold. The most distant objects in the universe, the very first galaxies, the very first stars, the moment when the cosmos transitioned from darkness to light, were effectively invisible to Hubble, hidden behind a wall of redshift that only an infrared telescope could penetrate. JWST was built to break through that wall, to see what was on the other side, to observe the cosmic dawn. The models were clear and confident about what it should find. Small, dim, irregular proto-galaxies, faint wisps of hydrogen and helium just beginning to collapse under gravity. The very first tentative attempts at structure formation in a universe that was still almost entirely dark. Tiny seeds that would, over the following billions of years, merge and grow into the galaxies we see today. Everything slow, everything gradual, everything hierarchical. That is what Lambda CDM predicted. That is what every numerical simulation, every theoretical calculation, every grant proposal and mission design document said would be waiting on the other side of the infrared wall. On July 11, 2022, President Biden stood at the White House and unveiled the first deep field image from JWST to a global audience. It was an observation of a galaxy cluster called SMACS 0723. In the southern constellation Volans, the image used the cluster's gravitational mass as a natural lens, bending and magnifying the light from more distant galaxies behind it. The total exposure time was 12.5 hours. Let me put that in perspective. 12.5 hours of JWST time produced an image that reached deeper into the universe than 100 hours of Hubble time had achieved in 1995, or 11.3 days in 2003, or 23 days of accumulated data in 2012. The jump in capability was not incremental. It was a leap across a chasm. Thousands of galaxies stretched and distorted into arcs by gravitational lensing, some of them among the most distant ever observed. The image was extraordinary. It was a technical triumph by every measure. The press celebrated it. The public marveled at it. Politicians pointed to it as proof that big science delivers. But behind the public celebration, in the offices and computer labs where the people who actually analyze this data do their work, something very different was happening. Because the data from the JWST survey, the JWST Advanced Deep Extragalactic Survey, and the CEERS program, the Cosmic Evolution Early Release Science Survey, was beginning to arrive. And what those surveys were finding did not match the predictions. It did not fit within the comfortable parameters of Lambda CDM. It did not even fit within the adjusted, stretched, already uncomfortable parameters that had been applied after the HUDF and XDF results. What JWST was finding was, by the standards of the existing model, impossible. The first person to sound the alarm by several published accounts was Erica Nelson at the University of Colorado, Boulder. Nelson was examining early JWST photometry of high redshift galaxy candidates when she spotted several objects that were too red and too bright for their inferred distances. She flagged them to her collaborator, Ivo Labe, at Swinburne University of Technology in Melbourne, Australia. Labe is a Dutch-born astronomer, PhD from Leiden, former Carnegie Fellow and NASA Hubble Fellow at Carnegie Observatories in Pasadena, who moved to Swinburne in 2018. He is known among colleagues for a combination of relentless scientific intensity and an unlikely devotion to surfing. He reportedly chose Swinburne over a position at his alma mater in Leiden, in part because of its proximity to Bells Beach, one of the most celebrated surf breaks in the Southern Hemisphere. He is the kind of person who names galaxies after Chinese mythological dragons and sends emails about spectral energy distributions at 3 a.m. He had spent his career pushing the boundary of the most distant known galaxies, repeatedly holding the record for the farthest object ever observed. He knew, better than almost anyone alive, what early galaxies were supposed to look like. These were not it. The objects Nelson had flagged were not subtly unusual. They were spectacularly wrong. The first thing that jumped out was the color. In astronomy, color is a proxy for the physical properties of a source. Blue objects are typically young, hot stars, or active galactic nuclei. Red objects are typically old stellar populations, dust-reddened sources, or very high redshift objects whose light has been stretched by cosmological expansion. These objects were red, very red, much redder than any known galaxy at their apparent distance. When Labbé's pipeline tried to fit them with standard galaxy models, the only solutions that could reproduce the observed colors placed the galaxies at extremely high redshifts with extremely large stellar masses. The software was essentially saying that these pinpricks of red light contained as many stars as the Milky Way, but existed in a universe that was less than 700 million years old. The natural assumption was that something had gone wrong. Calibration errors, contamination from foreground objects, incorrect background subtraction, artifacts of the new instrument. JWST was, at that point, only months into its science operations. Its calibration pipelines were still being refined. The data reduction procedures were still being optimized. There were legitimate reasons to suspect that the measurements might be wrong, and so the team checked. They checked everything. They reran the photometry with different apertures. They modeled the background with different techniques. They examined the JWST point spread function for artifacts. They compared the pipeline outputs to simulated data with known inputs. They looked for foreground contamination from Milky Way stars or nearby galaxies. They tested whether active galactic nuclei could mimic the observed colors. They spent months trying to make the measurements go away. The measurements did not go away. They were robust, and as additional JWST programs came online, as more data accumulated from different surveys, different instruments, different pointings, more objects like them appeared. They were not flukes. They were a population. Labbé ran his spectral analysis pipeline on the candidates Nelson had flagged. The software compares the observed light from an object across multiple wavelength bands to models of stellar populations at different ages, masses, and redshifts, and returns the best fitting parameters. When the results came back, Labbé later described his reaction in the conversation. He said he ran the analysis on a tiny pinprick of light, and it returned two numbers: distance, 13.1 billion light-years, mass, 100 billion stars. And I nearly spit out my coffee, he wrote. We just discovered the impossible. Impossibly early, impossibly massive galaxies. The objects Nelson had flagged were at redshifts between approximately 7 and 9, meaning they existed between 500 and 700 million years after the Big Bang. High redshift galaxies were not new. Hubble had found them. The problem was not the distance. The problem was the mass. When Labbé fit the photometric data to stellar population models, the implied stellar masses came back at 10 to the 10th solar masses. Some reached 10 to the 11th. 10 to the 11th solar masses is 100 billion times the mass of the Sun. That is the stellar mass of the Milky Way. Our galaxy, the product of 13.8 billion years of hierarchical assembly, of thousands of smaller galaxies merging and combining over cosmic time. And here were objects with the same mass, fully assembled, sitting in the universe when it was less than 5% of its current age. Under Lambda CDM, this is not just unlikely. If the masses are correct, it is physically impossible. The reason is math, and the math is unforgiving. After the Big Bang, the universe was a hot, dense plasma of hydrogen, helium, and dark matter. As it expanded and cooled, the dark matter collapsed first, pulled together by gravity into structures called halos. Ordinary matter, baryons, fell into those gravitational wells and began collapsing into stars. Lambda CDM predicts with precision how massive those dark matter halos can be at any given time in cosmic history. And from the mass of the halo, you can calculate the maximum amount of baryonic matter available to form stars. The baryon fraction is set by cosmological measurements. It is about 16% of the total mass of any halo. The maximum amount of stellar mass you can produce is therefore 16% of the halo mass, and that is only if you assume a 100% baryon to star conversion efficiency. Every single available atom of hydrogen and helium turned into a star, with zero gas left over, zero feedback, zero ejection, zero inefficiency. In practice, the real efficiency in observed galaxies is far lower, around 10 to 20%, because supernova explosions, stellar winds, and radiation pressure blow gas out of galaxies and prevent it from forming stars. You cannot beat the physics. And for Labbé's galaxies to have the masses his pipeline was reporting, the efficiency would have to be not 10%, not 50%, but in some cases greater than 100%. More stars than there were baryons available to build them from. Labbé published the results in Nature in February 2023. The paper is titled "A Population of Red Candidate Massive Galaxies Approximately 600 Million Years After the Big Bang." It reported 6 candidate massive galaxies with stellar masses above 10 to the R. 10th solar masses had redshifts 7.4 to 9.1. One appeared to have a mass of roughly 10 to the 11th solar masses. The stellar mass density at these redshifts was, in the paper's words, a factor of 10 to 30, higher than previous UV-selected surveys had found. Labbé's co-author, Joel Leger, at Penn State gave them the name that stuck. He called them universe breakers. And the quote he provided captures the scale of the problem precisely. We have been informally calling these objects universe breakers, and they have been living up to their name so far. The known mass in stars at this period of our universe is up to 100 times greater than we had previously thought. Even if we cut the sample in half, this is still an astounding change. 100 times, not 10% more, not double, 100 times greater than what the standard model of the universe says should be there. And Leger acknowledged that even if half the sample was wrong, even if 3 of the 6 galaxies were explained away by calibration errors or misidentified redshifts or contamination from active galactic nuclei, the remaining 3 still constituted a problem that Lambda CDM cannot solve without violating its own foundational constraints. Simultaneously, a theorist at the University of Texas at Austin named Michael Boylan-Kolchin was doing the math that would turn this from an observational surprise into a theoretical crisis. Boylan-Kolchin published a paper in Nature Astronomy in June 2023 that is one of those rare academic publications that reads less like a research article and more like an indictment. He did not propose a solution. He did not suggest a patch or an adjustment. He did the thing that theoretical physicists are supposed to do and almost never actually do when the data threatens the paradigm. He calculated exactly how badly the data violated the predictions. His approach was ruthlessly simple. He asked one question. At any given redshift, what is the absolute maximum stellar mass that Lambda CDM allows, even under the most generous possible assumptions? Even if you assume 100% baryon to star conversion, even if you ignore all feedback, Even if every baryon in every halo becomes a star, what is the theoretical ceiling? Then he compared that ceiling to the observed masses reported by Lambda. The result was devastating. The most massive galaxies in Lambda's sample exceeded the absolute maximum allowed by Lambda CDM by more than a factor of 20. Not 20%, a factor of 20. And this is the ceiling, assuming 100% efficiency, which is itself a physical impossibility in any realistic model. In practice, with realistic feedback, the actual discrepancy is far larger. The data did not just strain the model. It exceeded the model's theoretical maximum by an order of magnitude. There is no parameter within Lambda CDM that you can turn to make this work. The framework itself does not have room for what JWST observed. And then, in January of 2024, things got worse. A team led by Stefano Carniani at the Scuola Normale Superiore in Pisa, Italy, pointed the NIR spec instrument on JWST at a tiny candidate galaxy that had been flagged in the JWST survey. Carniani is a young astronomer, an Italian who did his doctorate at the University of Florence, did postdoctoral work at the Cavendish Astrophysics Group in Cambridge, England, and holds an ERC starting grant for a project called WING, studying galactic winds. He is part of the NIR spec Guaranteed Time Observations team and was one of the architects of the JWST survey strategy. He had designed the spectroscopic observations that were now pointing at this candidate galaxy, collecting roughly 10 hours of integration time. What came back was a spectroscopic confirmation. The galaxy, designated JWST Zone 4, 0, existed at a redshift of 14.32, later refined to 14.1796, with a remarkably small uncertainty. That redshift translates to approximately 290 million years after the Big Bang. Not 700 million years like Labbé's universe breakers, not 500 million years, 290. The universe was barely 2% of its current age, and this was not a point source. It was not a quasar or a bright accretion disk around a black hole that might be masquerading as a galaxy. It had a measured half-light radius of 260 parsecs, meaning it was spatially resolved, meaning the light was demonstrably coming from an extended structure on the sky, not from a single luminous point. Its ultraviolet absolute magnitude was negative 20.81, making it extraordinarily luminous for any galaxy at any epoch, let alone one that existed less than 300 million years after the origin of everything. Its inferred stellar mass was roughly 500 million solar masses. And ALMA, the Atacama Large Millimeter Array, detected emission from doubly ionized oxygen at 88 microns, implying a gas phase metallicity of approximately 17% solar. That oxygen could only have been created by nuclear fusion inside the cores of massive stars, then dispersed into the surrounding gas when those stars exploded as supernovae. For this galaxy to contain that much oxygen at that age means that not one generation, but multiple generations of massive stars had already lived their full lives, exploded, seeded the gas with heavy elements, and the enriched gas had already collapsed again to form new stars incorporating those elements, all within 290 million years. Carniani's assessment, published in the NASA and ESA press release accompanying the results, was diplomatic in tone, but devastating in substance. He wrote, "All these observations together tell us that JWST Zone 4, 0 is not like the types of galaxies that have been predicted by theoretical models and computer simulations to exist in the very early universe." On the quality of the data, he added, "These are by far the faintest infrared spectra ever taken. in the language of academic science, saying that an observation matches no existing theoretical prediction is as close as a professional astronomer gets to saying every model is wrong. I want to stop here and correct a misconception that I see in nearly every popular account of the JWST crisis, because it makes the problem seem more solvable than it actually is. The misconception is that the issue is primarily about mass, that the galaxies are too heavy, and that if we could find a way to make them appear less heavy, through a different initial mass function, through active galactic nucleus contamination, through photometric errors, the crisis would be resolved. That is wrong. The mass problem is one dimension of the crisis, and it is arguably not the most severe one. The chemical enrichment is worse, and I need to explain why, because this is the part that most accounts gloss over, and it is the part that matters most. The stellar mass of a galaxy is, in principle, revisable. It is inferred from the galaxy's photometry, the amount of light it emits at different wavelengths, by fitting that light to models of stellar populations. Change the assumptions about the stellar population, change the assumed initial mass function, change the dust model, change the star formation history, and the inferred mass changes. These are model-dependent inferences. They can be debated. They can be revised downward if the assumptions turn out to be wrong. But the oxygen in Jade's GS zone 4, 0, is not a model-dependent inference. It is a direct measurement. The ALMA telescope detected a specific emission line at a specific wavelength, the 88-micron line of doubly ionized oxygen, which is produced when oxygen atoms in a particular ionization state emit a photon at a known frequency. That line is either present or it is not. It is present. The measurement is real, and the amount of oxygen required to produce the observed emission implies that a significant population of massive stars had already formed, had already lived their entire lives, which for massive stars means millions of years, not billions, had already exploded as core collapse supernovae, had already dispersed the oxygen and carbon and silicon forged in their interiors into the surrounding interstellar gas, and the gas enriched by those explosions had already cooled, collapsed, and formed a new generation of stars. All of this entire cycle of stellar birth, death, enrichment, and rebirth had to have occurred multiple times within 290 million years. To put that in perspective, the most massive stars in the universe, the ones that produce the most oxygen per unit mass, live for only a few million years. They burn hot and die fast. But after they explode, the enriched gas they eject does not immediately form new stars. It has to mix with the surrounding medium, cool radiatively, collapse under gravity, fragment into dense cores, and ignite new stellar nuclear fusion. That process takes tens of millions of years in the best case. Several cycles of this, each taking tens of millions of years, have to fit within 290 million years, minus the time it takes for the first dark matter halos to form and for the first gas to collapse into the very first generation of stars. That first generation had to form from pristine, metal-free gas, which cools slowly and is believed to produce primarily very massive stars. Those first stars had to live, die, and enrich the gas before the first metal-enriched stars could form. The timeline is agonizingly tight. And 17% solar metallicity is not a trivial amount of enrichment. It represents a substantial buildup of heavy elements, the kind of buildup that in the local universe takes hundreds of millions to billions of years. You cannot make this problem go away by adjusting the photometric calibration. You cannot wave it off with a different initial mass function. The oxygen is real. The timeline is real. The physics of stellar evolution and chemical enrichment is among the best understood areas of astrophysics, and the timeline does not work. But the impossible galaxies were not the only thing JWST found. There was something else in the deep field data, something that nobody had predicted, nobody had modeled, nobody had even theorized might exist. Scattered across the images at redshifts between 4 and 8 were hundreds of tiny, compact red objects. They had no precedent in Hubble data. They had no analog in any existing catalog or simulation. And when astronomers started collecting spectra of them, the results deepened the crisis in ways that made the universe breakers look like a warm-up act. They are called little red dots, and the name was given to them in a paper published in March 2024 in the Astrophysical Journal by Jorrit Matthij and colleagues. Matthij, working at the Institute of Science and Technology, Austria, had been studying faint, active galactic nuclei using data from the EIGIR and FRESCO JWST surveys. His team identified 20 objects with broad hydrogen alpha emission lines at redshifts between 4.2 and 5.5. The line widths ranged from 1,200 to 3,700 kilometers per second, characteristic of gas orbiting an extremely massive compact object. The implied central masses were 10 to the 7th to 10 to the 8th solar masses, millions to hundreds of millions of times the mass of the Sun. Supermassive black holes at the hearts of what appeared to be compact, peculiar galaxies, with a spectral shape unlike anything observed before. Blue in the ultraviolet, red in the optical, a V-shaped spectral energy distribution with a distinctive Balmer break, and their number densities approximately 10 to the -5th per cubic co-moving megaparsec, were about 10 times higher than the extrapolation of known quasar luminosity functions to those magnitudes. There were 10 times more supermassive black holes at these redshifts than any model had predicted. By 2025, over 340 little red dots had been catalogued across multiple JWST surveys, 340 objects that exist in no prediction, no simulation, no theoretical framework that was written before JWST looked into the dark and found them there. Vasily Kokorev, then working between the University of Texas at Austin and the University of Copenhagen, published a study in the Astrophysical Journal Letters in June 2024, showing that the black holes inside the little red dots are not just massive for their epoch, they are grotesquely overmassive relative to their host galaxies. In the local universe, there is a well-established scaling relationship between the mass of a galaxy's central supermassive black hole and the mass of the galaxy's stellar bulge. This is one of the most robust empirical relationships in extragalactic astronomy. It holds across a vast range of galaxy types and masses. The little red dots violated by 2 orders of magnitude. Their central black holes are approximately 100 times more massive relative to their host stellar populations than the local relationship predicts. The black holes grew too fast. The galaxies grew too slow. Or something about the physics of the early universe produced a relationship between black holes and galaxies that is completely unlike what we observe today. I need to explain why this is worse than it sounds, because the numbers alone do not capture the physical impossibility. There are hard limits on how fast a black hole can grow. When gas falls toward a black hole, it does not just plunge straight in. It forms a swirling disk of material called an accretion disk. Friction and compression within that disk heat the gas to millions of degrees, producing intense radiation. That radiation exerts an outward pressure on the infalling material. At a certain accretion rate, the outward radiation pressure exactly balances the inward gravitational pull, and no additional gas can fall in. This threshold is called the Eddington limit, named after Arthur Eddington, who first calculated it in 1926. It sets an absolute maximum on the rate at which a black hole can consume matter through standard disk accretion. The math is straightforward, but the implications are devastating. To grow a black hole from a stellar remnant seed of, say, 100 solar masses, the kind of object left behind when a very massive star collapses at the end of its life, to a supermassive black hole of 100 million solar masses, accreting continuously at the Eddington limit, with no interruptions, no mergers, no feedback disruptions, no quiescent periods, requires roughly 800 million years. 800 million years of perfectly sustained maximum rate growth. Now consider the little red dots. Many of them exist at redshifts between 5 and 8, when the universe was between 700 million and 1.3 billion years old. After subtracting the first few 100 million years, when the universe was too hot and dense for any structure to form, the available growth window is, at best, about 700 million years. Under the most generous assumptions, with continuous Eddington limited accretion from the earliest possible moment, you can barely grow 100 solar mass seed to the masses observed in the little red dots. Under realistic assumptions, with the interruptions and variability that every real astrophysical system experiences, you cannot. So either the seed black holes were much heavier than stellar remnants, which requires the direct collapse mechanism and its associated improbabilities, or the black holes grew at rates exceeding the Eddington limit for sustained periods, which is possible in principle but extraordinarily difficult to maintain physically, or the black holes formed and grew through a mechanism that our current physics does not describe. None of these options is comfortable, and none of them fully resolves the problem when combined with the other JWST anomalies. And in November 2025, the mystery deepened further. A paper by Hiding and colleagues in astronomy and astrophysics, based on data from the Ruby survey co-led by Anna de Graaf at the Harvard-Smithsonian Center for Astrophysics and Gabriel Brammer at the Cosmic Dawn Center in Copenhagen, described an object they called the cliff. It is a little red dot at redshift 3.55, with a Balmer break so steep, a drop in flux at a specific wavelength so extreme that no combination of standard stellar population models can reproduce it. The authors tried every configuration of stellar age, metallicity, dust, and star formation history available in current modeling codes. None of them fit. The cliff appears to require either a completely unknown type of stellar population or a physical process that has no current theoretical description. And it is sitting there, in the data, defying explanation. I want to make sure you have the full picture of where this stands, because the scale of the problem gets lost when you describe it piece by piece. The universe breaker galaxies require baryon to star conversion efficiencies that exceed the physical maximum imposed by cosmological constraints. JADE's GS Zone 4.0 is a spatially resolved, chemically enriched galaxy that no model predicted and no simulation has reproduced. The little red dots contain supermassive black holes, 100 times too massive for their host galaxies, in numbers 10 times higher than any prediction. And at least one of them has spectral properties that cannot be explained by any existing physical model. Each of these findings alone would be a serious challenge to Lambda CDM. Together, they are not a series of challenges. They are a systematic failure of prediction across every observable quantity: mass, luminosity, number density, chemical enrichment, spectral shape, assembly timescale. Every single thing the models predicted about the first billion years has been wrong, and it has been wrong in the same direction every time. The universe did more, faster, than we said it could. So the obvious question is, if the predictions are this wrong, Why has nobody fixed the model? And here is where I personally struggled with this material. Because the answer is not that nobody has tried. Everybody has tried. And none of the fixes work. Not fully. Not convincingly. Not in a way that resolves all the data without creating new problems. Let me walk through them, because each failure tells you something important about how deep this problem goes. The first proposed fix is the top-heavy initial mass function. The initial mass function describes the distribution of stellar masses when a new generation of stars forms. In the local universe, it follows a pattern measured by Edwin Salpeter in 1955, a power law where low-mass stars vastly outnumber high-mass stars. The idea is that, in the early universe, conditions might have favored more massive stars. More massive stars produce more ultraviolet light per unit of stellar mass. If the early IMF was top-heavy, early galaxies would appear more luminous and more massive in photometric surveys than they actually were. The inferred masses would be overestimates. The crisis would soften. This partially works. Mauerhofer and Dayal, using the Astrea simulation framework, published a paper in 2024 showing that a moderately top-heavy IMF could reproduce JWST's observed ultraviolet luminosity functions at redshifts above 10. But in January 2025, a team led by Cheng, using spectroscopic data from the JWST IMF ERNO program, measured the IMF in quiescent galaxies at redshift 0.7. These are the direct descendants of the impossibly early JWST galaxies, the systems those galaxies should evolve into over the following billions of years. If the ancestors had a top-heavy IMF, the descendants should carry the chemical fingerprints of all those extra massive stars. What Cheng's team found was the opposite. The IMF in the descendant galaxies is not top-heavy, it is bottom-heavy. More low-mass stars than the Salpeter function predicts. Not fewer, and the bottom-heavy IMF increases the inferred stellar masses of the early galaxies by a factor of 3 to 4. The fix did not solve the problem. It made it worse. The second proposed fix is direct collapse black hole seeds. Instead of starting from small stellar remnant black holes of a few solar masses that must then grow by accreting gas over hundreds of millions of years, maybe the black holes in the little red dots started big. In specific pristine environments, a massive cloud of primordial gas could bypass star formation entirely and collapse directly into a black hole of 10,000 to 100,000 solar masses. These heavy seeds would reach supermassive scales much sooner. In February 2026, Fabio Pacucci and colleagues published radiation hydrodynamic simulations showing that direct collapse black holes, wrapped in dense cocoons of ionized gas, could naturally explain many unusual spectral properties of the little red dots. This is promising work, but it does not address the stellar-dominated galaxies. Jade's GS Zone 4, 0, is resolved at 260 parsecs. Its light comes from stars. You cannot explain an impossibly massive stellar population with a different black hole formation mechanism. The stars are still there. The oxygen is still there. The time is still too short. The third fix is early dark energy. The most ambitious proposal. Shen, Vogelsberger, Boylan-Kolchin, Takchela, and Naidu published a paper in the monthly notices of the Royal Astronomical Society in 2024, arguing that if the early universe contained a transient form of dark energy that has since decayed, it would change the expansion history in ways that alter the halo mass function and allow more massive structures to form earlier. This is appealing because it potentially solves two problems at once: the JWST mass tension and the Hubble tension. The persistent disagreement between the locally measured expansion rate of 73 kilometers per second per megaparsec and the CMB-derived value of 67.4. But even with early dark energy, the models still need elevated star formation efficiencies and significant scatter in the ultraviolet luminosity function to match the data. Every additional free parameter reduces the predictive power of the theory, and the theory has not been confirmed. It is proposed. The fourth fix is feedback-free starbursts, proposed by Avishai Dekal and colleagues in 2023. The idea is that in extremely dense early universe environments, gas collapse is so fast that stars form before the first supernovae can explode and blow the remaining gas away. If the free-fall time is shorter than the supernova delay time, you can achieve near 100% baryon to star efficiency in short, intense bursts. Clever, but unconfirmed observationally, and it requires halo conditions that are themselves at the edge of what Lambda CDM predicts. The fifth fix is bursty or stochastic star formation. Maybe early galaxies flickered, alternating between intense star-forming episodes and quiet periods. If we catch them during a burst, they look brighter and more massive than they really are, on average. This helps with the luminosity function, but cannot explain the spectroscopically confirmed masses or the chemical enrichment of Jade's GS zone 4, 0. You cannot fake 17% solar metallicity with a temporary burst of star formation. That oxygen had to be forged inside stars that already lived and died. There is a misconception that I want to correct here, because I see it in nearly every popular account of the JWST crisis, and it is a misconception that makes the problem seem more solvable than it actually is. The misconception is that the issue is just about mass, that the galaxies are too heavy, and that if we could find a way to make them appear less heavy, through a different IMF, through AGN contamination, through photometric errors, the crisis would be resolved. That is wrong. Mass is one dimension of the problem, and it is arguably not even the most serious one. The chemical enrichment is worse, because the stellar mass of a galaxy can, in principle, be revised downward if you change your assumptions about the stellar population. Maybe the stars are different. Maybe the light-to-mass ratio is different. Maybe we are misinterpreting the photometry. These are legitimate concerns, and they have been explored extensively. But the oxygen in Jade's GS zone 4, 0 is not a model-dependent inference. It is a direct detection. ALMA measured the 88-micron emission line of doubly ionized oxygen. That line is either there or it is not. It is there, and the amount of oxygen required to produce the observed line flux implies that a substantial population of stars, massive stars, had to have formed, burned through their fuel, exploded as supernovae, and dispersed their nucleosynthetic products into the surrounding gas, all within the first 290 million years of cosmic history. You cannot fake that with a different IMF. You cannot make it go away with better photometric calibration. The oxygen is real. The stars that made it were real. And the timeline in which they had to have existed is genuinely, unambiguously too short for any existing model of star formation to explain. That is the part of this crisis that does not get enough attention. The spectroscopic confirmations are harder to dismiss than the photometric estimates, and they keep coming in, each one adding another data point to a picture that is increasingly difficult to reconcile with the theoretical framework. And then there is the sixth and most recent attempt, the one that made headlines. In January 2026, Vadim Rusakov and Darach Watson at the Cosmic Dawn Center in Copenhagen published a paper in Nature titled "Little Red Dots as Young Supermassive Black Holes in dense ionized cocoons. Their argument was that the broad hydrogen emission lines used to infer the masses of the little red dots' central black holes were being broadened not by orbital velocity, but by electron scattering. Photons bouncing off free electrons in a dense ionized gas shell get their wavelengths spread out, mimicking the broad lines produced by fast-orbiting gas. If the broadening is from electron scattering rather than orbital motion, the actual black hole masses are about 100 times lower than initially estimated. Watson described it as follows. The little red dots are young black holes, 100 times less massive than previously believed, enshrouded in a cocoon of gas, which they are consuming in order to grow larger. The same day, independent papers by Rohan Naidu at MIT and Anna de Graaf at Harvard reached compatible conclusions through different analysis methods, 3 teams, 3 independent analyses, 1 converging answer. I want to be honest about this, because intellectual honesty matters more than narrative convenience. The Rusakov paper is genuine progress. It is a plausible, testable, physically motivated explanation for a significant fraction of the little red dot population. If it holds up under further scrutiny and observational confirmation, a major piece of the puzzle might be resolved through conventional astrophysics without invoking new fundamental physics. But, and this is the but that carries the weight of the entire story, the little red dots were never the whole problem. They were the most dramatic symptom, the most photogenic anomaly, the headline grabber. But the underlying disease is older, deeper, and more resistant to treatment than the little red dots, and it has not been cured. JD's GS zone 4, 0, is still there. 290 million years after the Big Bang. Spatially resolved, chemically enriched, multiple generations of stellar evolution complete, not a black hole in a cocoon. A galaxy with stars and oxygen, and structure that no model can reproduce. The Lambda galaxies are still there, even after accounting for possible AGN contamination, even after MIRI photometry revisions that brought some of the masses down. The cumulative stellar mass density at redshift 8 still requires baryon to star conversion efficiencies of around 30%, 1.5 to 3 times higher than anything observed at any later epoch, and the pattern that started in 1995 continues without interruption. Each deeper look finds more than the models predict. Each revision goes in the same direction. Each proposed fix addresses one piece of the puzzle, while leaving the rest intact or making it worse. Top-heavy IMF helps luminosities, but descendant IMF data worsens masses. Direct collapse helps black holes, but not stellar galaxies. Early dark energy helps the mass function, but needs extra parameters. Feedback-free starbursts help efficiency, but lack confirmation. The cocoon model helps little red dots, but not anything else. There is no single solution that resolves all the data simultaneously. Every fix trades one problem for another. There is a phrase in the philosophy of science for what happens when a theory survives by accumulating auxiliary hypotheses, each one designed to save it from the latest disconfirming observation. It is called a degenerating research program. The phrase comes from the philosopher Imre Lakatos. A research program is degenerating when it stops making novel predictions and instead spends all its energy explaining away anomalies after the fact. I am not claiming Lambda CDM has reached that point. There are smart, careful people working on each of these proposed fixes, and some of them may turn out to be correct. But the trajectory, the direction of travel over 23 years, the consistent pattern of observations exceeding predictions and fixes failing to fully close the gap, should give anyone paying attention serious pause. And then there is the Hubble tension, which connects to all of this in a way that most popular accounts either miss entirely or mention as a footnote. But it is not a footnote. It is possibly the most important thread in the entire story because it suggests that the problem with Lambda CDM is not limited to the early universe. It may be woven into the fabric of the model itself. Here is what the Hubble tension is. There are two ways to measure how fast the universe is expanding. The first is the local method. You measure the distances to nearby galaxies using a chain of cosmic yardsticks, Cepheid variable stars whose brightness pulsates at a rate directly related to their intrinsic luminosity, then Type Ia supernovae, thermonuclear explosions of white dwarf stars that all reach approximately the same peak brightness, which lets you use them as standard candles out to distances of billions of light years. You compare these distances to the recession velocities of the galaxies, measured from the redshift of their light, and you get a number called the Hubble constant, h0, the current rate of expansion. The SH0ES team, led by Adam Rees at Johns Hopkins, has been refining this measurement for over 2 decades. Their current best value, published in 2022, is 73.04, plus or minus 1.04 kilometers per second per megaparsec. That is a precision of about 1.5%. It is the most precise local measurement of the expansion rate ever made. The second method is the cosmic microwave background method. You observe the relic radiation from the Big Bang, the afterglow of the hot plasma that filled the universe 380,000 years after its birth. And you use the patterns in that radiation, the tiny fluctuations in temperature and polarization, to infer the properties of the universe at that epoch. From those properties, using Lambda CDM as your theoretical framework, you can extrapolate forward in time to calculate what the expansion rate should be today. The Planck satellite, which mapped the CMB with unprecedented precision, gives a value of 67.4 plus or minus 0.5 kilometers per second per megaparsec. The discrepancy between these two numbers, 73 from the local measurement and 67 from the CMB extrapolation, may not sound dramatic. It is about 8%. But in science, significance is not about the size of the discrepancy. It is about the size of the error bars. Both measurements have been refined to the point where their error bars do not overlap. The disagreement is now above 5 sigma, which is the threshold particle physicists use to declare a discovery. A 5 sigma discrepancy means there is less than a 1 in 3.5 million chance that the disagreement is a statistical fluke. Both numbers cannot be correct. Either the local measurement is wrong, or the CMB measurement is wrong. Or Lambda CDM, the model used to connect the CMB measurement to a prediction for the present-day expansion rate, is wrong. For years, a leading hypothesis was that the local measurement was suffering from a subtle, systematic error. The most commonly cited candidate was Cepheid crowding. In distant galaxies, the Cepheid variable stars used as the first rung of the distance ladder are faint, and the images are blurred by Hubble's limited resolution. Nearby stars that are not Cepheids can contaminate the photometry, making the Cepheids appear brighter than they actually are, which makes the galaxies appear closer, which makes the expansion rate appear faster. It was a reasonable concern, and JWST was perfectly positioned to test it, because its infrared resolution is sharp enough to separate the Cepheids from their neighbors with far greater precision than Hubble. In 2024, Adam Rees and colleagues published the result of that test in the Astrophysical Journal Letters. The title of the paper tells you everything you need to know. It begins with JWST observations reject unrecognized crowding of Cepheid photometry. They observed Cepheids in a supernova host galaxy, NGC 4258. At infrared wavelengths, where the JWST images are clean enough to separate every Cepheid from its neighbors. The Hubble distances were confirmed. The crowding hypothesis was not just disfavored, it was eliminated. The paper states, and I want you to hear the precision of this language, we can reject the hypothesis of unrecognized crowding of Cepheid photometry from HST that grows with distance as the cause of the Hubble tension at 8.2 sigma confidence, greater confidence than that of the Hubble tension itself. 8 sigma, the systematic error that was supposed to explain the tension, is not there. The tension is real, and it has no explanation within Lambda CDM. In 2025, Rias's team published an updated measurement combining JWST and HST Cepheid data, arriving at 73.49 plus or minus 0.93 kilometers per second per megaparsec. Even more precise, even more inconsistent with Planck. The problem is not going away. It is getting sharper. And here is where the Hubble tension connects to the impossible early universe. Both problems point to the same part of the model. Both problems suggest that Lambda CDM's description of the early universe, its account of how the cosmos expanded and how structure formed in the first few billion years, is missing something. The early dark energy proposal that the Shen team has been developing is explicitly designed to address both tensions simultaneously. If there was a form of dark energy in the very early universe that has since decayed, it would change the expansion history in a way that produces a higher present-day expansion rate, matching the local measurement, while also changing the halo mass function in a way that allows more massive galaxies to form earlier, matching the JWST data. 1 modification. 2 crises resolved. That is what makes the idea so seductive and so unsettling at the same time. Because if early dark energy is real, it means that the first billion years of the universe contained a form of energy that has completely vanished, leaving no direct trace in the present-day cosmos. We missed it for a century. And everything we calculated about the early universe was wrong because we did not know it was there. And the new data keeps arriving, reinforcing the same pattern. In 2025, a galaxy nicknamed Zhulong, after a dragon of Chinese mythology, was identified in JWST data as a Milky Way mass disk galaxy at a redshift of approximately 5. That means it existed when the universe was about 1.2 billion years old. A disk galaxy of that mass at that epoch requires a baryon-to-star conversion efficiency of around 30%. That is 1.5 times higher than the most efficient galaxy formation ever observed at any later epoch. 1.5 times the best-case scenario at a time when the universe was less than 10% of its current age. Zhulong is not at the extreme frontier of redshift 14 like JWST Zone 4. 0. It is not breaking the absolute ceiling the way Labbé's universe breakers did, but it is continuing the trend at intermediate redshifts, showing that the efficiency problem is not confined to the very first galaxies. It extends across the entire first 2 billion years. The early universe was running hotter, faster, and more efficiently than Lambda CDM predicts, everywhere, at every epoch, not just at the extreme edge. And the DSI survey, the Dark Energy Spectroscopic Instrument, which began collecting data in 2021 and published its first cosmological results in 2024, has added another thread to this tapestry. DESI is mapping the three-dimensional positions of tens of millions of galaxies to measure the history of cosmic expansion using baryon acoustic oscillations, ripples in the distribution of galaxies that serve as a standard ruler. The early DESI data hints that dark energy may not be constant. It may be changing over time. If confirmed, this would directly undermine the lambda, the cosmological constant in Lambda CDM, which assumes dark energy has the same density at all times. A varying dark energy would connect to the early dark energy hypothesis, suggesting that whatever is accelerating the expansion of the universe today may be a descendant or an echo of the force that was active in the first billion years and then vanished. The pieces of a much larger puzzle are beginning to assemble themselves, and they are not assembling into the picture that was on the box. And here is where this stops being about telescopes and starts being about you. Because Lambda CDM is not an abstract framework that physicists debate at conferences. It is the model that tells you what kind of universe you live in. It is the model behind every documentary you have ever watched about the cosmos, every textbook diagram of the Big Bang, every infographic about the timeline of the universe, the one with the expanding cone and the little labels marking the formation of atoms, the first stars, the first galaxies, the emergence of Earth. That timeline is derived from Lambda CDM. The ages are derived from Lambda CDM. The sequence is derived from Lambda CDM. When someone tells you the universe is 13.8 billion years old, that number comes from fitting the cosmic microwave background data with the Lambda CDM model and extracting the best fit age parameter. It is not a direct measurement. It is a model-dependent inference. If the model is wrong, the number could be different. When someone tells you the universe is 5% normal matter, 25% dark matter, and 70% dark energy, those percentages come from Lambda CDM. They are not independently measured to that precision. They are extracted from the CMB data within the framework of a specific model. If the framework is wrong, the percentages could be different. When someone tells you the universe will expand forever, growing colder and darker until the last stars die out trillions of years from now, that prediction comes from extrapolating the Lambda CDM model into the far future, assuming that the dark energy behaves as a cosmological constant, that its density stays the same even as space expands. If the dark energy has a different nature than the model assumes, if it changes over time, if it is related to the early dark energy that may have existed in the first billion years and then vanished, then the long-term fate of the universe could be qualitatively different from what the model predicts. Not just quantitatively different, qualitatively different, a different ending, a different trajectory, a different answer to the question of whether everything ends in ice or fire or something else entirely. Those are not just numbers in a textbook. That is the story you were told about where you are, what you are part of, how everything began, and how everything will end. It is the cosmological narrative of your existence. And if the model that produces that narrative is fundamentally wrong about the first billion years, if the trend that has been pointing in the same direction for 23 consecutive years of progressively deeper observations is pointing where it appears to be pointing, then we genuinely do not know those things with the confidence we have been claiming. The age of the universe might be different. The composition might be different. The fate might be different. The story might be wrong. Think about what that means when you look up at the sky tonight. Every star you can see is in our galaxy. Beyond those stars, invisible to the naked eye, there are 2 trillion galaxies. We know that because Williams pointed a telescope at a grain of sand and found 3,000 of them. But the galaxies you cannot see, the ones at the edge of the observable universe, the ones that existed in the first few 100 million years, those galaxies are the ones that are causing the crisis. They are the ones that should not be there, that should not be so massive, so luminous, so chemically enriched, so structurally complete. And they are not distant abstractions. They are part of the causal chain that led to you. The heavy elements forged in those impossibly early stars, the carbon and oxygen and iron scattered by those impossibly early supernovae. That material ended up in later generations of galaxies, in later generations of stars, in the planets that formed around those stars, in the chemistry of life itself. If the universe made those elements faster and more efficiently than we thought, then the chemical history of the cosmos, the story of how the building blocks of life were assembled and distributed, is not the story we have been telling. It is a different story, a faster story, a story in which the universe was more capable, more productive, more creative in its first billion years than we gave it credit for. And there is something in that realization that I find not nihilistic, but genuinely humbling. The universe is not smaller than we thought. It is bigger. It is not simpler than we thought. It is more complex. It is not slower than we thought. It is faster. The story is not worse. It is stranger. And stranger, in science, has always turned out to be more interesting than the comfortable version. I want to be careful here, because I think there is a version of this argument that slides into nihilism, and that is not where the data leads. Lambda CDM is not entirely wrong. It describes the cosmic microwave background with extraordinary precision. It predicts the large-scale distribution of galaxies, the baryon acoustic oscillation signal, the abundance of light elements from Big Bang nuclear synthesis, all with impressive accuracy. These successes are real, and they are not going away. Whatever replaces Lambda CDM or modifies it will need to reproduce all of these successes while also accommodating the JWST data and the Hubble tension. That is a tall order. And the fact that no existing proposal can do it cleanly, that every fix helps in one domain while creating problems in another, tells you that the real answer has not been found yet. The data is ahead of the theory. The observations have outrun the models. And that is a genuinely unusual situation in modern physics. Usually, the theory leads and the observations confirm. Here, the observations are leading, and the theory is struggling to keep up. What I think we are watching right now, in real time, is the early stages of a paradigm shift. Not the kind that gets declared in a single dramatic paper or a single Nobel Prize speech. The slow kind, the kind where the data accumulates, the anomalies pile up, the patches multiply, and gradually, over years or decades, the community pivots from defending the old framework to constructing a new one. We are somewhere in the middle of that process. The anomalies are catalogued. The patches are proliferating. The old guard is defending the framework with legitimate science. The younger researchers are starting to ask louder questions. And the data keeps coming in. From JWST, from the DESI survey, from the Euclid Space Telescope, from ALMA and the Vera C, Rubin Observatory, each new dataset adding another tile to a mosaic that is starting to look very different from what was expected. The most disturbing element of this entire story is not any individual data point. It is the pattern. Every increase in observational capability has produced the same result. We look deeper, we find more than we expected. We adjust, we look deeper again, we find more again. We adjust again. And with each cycle, the adjustments grow larger, more desperate, more loaded with auxiliary assumptions, and the gap between prediction and reality gets wider, not narrower. At some point, a pattern like this stops being a series of surprises and starts being evidence that the thing you are being surprised about was never right in the first place. Robert Williams, the man who stared at nothing and found everything, made a decision that the institution around him was unwilling to make. He looked where nobody else wanted to look. And what he found there, what has been growing more troubling with every successive year and every successive telescope that has followed his lead, is not a series of isolated anomalies. It is the universe telling us with increasing clarity that the story we have been telling ourselves about how it assembled itself is wrong. The first galaxies were not small, dim, fragile structures slowly building themselves from the bottom up over billions of years. They were enormous, luminous, chemically complex systems that appeared in the cosmic darkness faster than any physics we know should allow. The black holes at their centers grew faster than any accretion model can explain, and the objects that appeared alongside them, the little red dots, and the universe breakers, and the impossible galaxies, are not aberrations to be explained away by adjusting a free parameter. They are the universe showing us what it actually did, as opposed to what we calculated it should have done. I want to come back to the human element one more time, because I think there is something happening in the astronomy community right now that echoes what happened in Williams's conference room in 1995, and I think it matters. The community is splitting, quietly, along a fault line that has nothing to do with the science itself, and everything to do with how institutions process uncomfortable information. On one side are researchers who acknowledge the severity of the JWST data and are actively exploring whether fundamental revisions to Lambda CDM are needed. People like Boylan-Kolchin, who framed the stellar mass density problem with mathematical precision, like the Shen team, who are proposing early dark energy as a unified solution. These are people who are taking the trend line seriously and following it to its implications, even when those implications are uncomfortable and career-threatening. On the other side are researchers who are committed to finding solutions within the existing framework, who are working on feedback-free starbursts, bursty star formation, top-heavy IMFs, AGN contamination corrections, and the electron scattering reinterpretation of the little red dots. These are not bad faith actors. They are doing legitimate science, and some of their work, like the Rusakov cocoon model, is genuinely advancing our understanding. But the institutional incentive structure overwhelmingly favors this group. Grant committees are more likely to fund work that refines the existing model than work that replaces it. Journal referees are more receptive to papers that solve anomalies within Lambda CDM than papers that question Lambda CDM itself. Career advancement in cosmology is built on a foundation of Lambda CDM being correct. The people who build their careers on that foundation have a natural, human, understandable resistance to evidence that the foundation is cracked. This is not conspiracy. I want to be absolutely clear about that. Nobody is suppressing data. Nobody is hiding results. The papers are published. The data is public. The anomalies are acknowledged openly in the professional literature. But there is a difference between acknowledging an anomaly and acting on what it implies. And right now, the community is in the acknowledgement phase. The anomalies are catalogued. The tensions are quantified. The proposed fixes are proliferating. But the deeper question, whether the framework itself needs to be abandoned, is being deferred. It is being treated as premature. And maybe it is premature, but the trend line has not changed direction in 23 years. At some point, premature becomes overdue. And the longer the deferral lasts, the more work, the more careers, the more institutional credibility gets stacked on a foundation that the data is steadily undermining. There is a historical parallel here that I cannot help but think about. In the early 20th century, the prevailing model of the atom was the plum pudding model proposed by J.J. Thomson. Electrons were thought to be embedded in a diffuse cloud of positive charge, like raisins in a pudding. When Ernest Rutherford's team fired alpha particles at gold foil in 1911 and found that most passed through, but some bounced straight back, the result was incompatible with the plum pudding model. Rutherford famously compared it to firing a cannon shell at tissue paper and having it bounce back at you. The old model could not be patched. It had to be replaced. And it was replaced quickly because the data was unambiguous and the community was small enough that no massive institutional inertia opposed the change. Cosmology in the 21st century is different. Lambda CDM is not a simple model held by a small group. It is the foundation of an entire discipline, billions of dollars in infrastructure, thousands of careers, decades of accumulated work. The social cost of replacement is not zero, and social cost, whether we like to admit it or not, affects how quickly scientific communities process paradigm-threatening data. I am not claiming Lambda CDM is wrong in the way the plum pudding model was wrong. The analogy is imperfect. Lambda CDM has enormous predictive successes, especially in describing the cosmic microwave background and the large-scale distribution of galaxies. But the high redshift predictions, the part of the model that describes the first billion years, the part that tells us how the universe transitioned from a smooth, hot plasma to the structured, galaxy-filled cosmos we observe. That part is failing observational tests. Repeatedly, consistently in the same direction, and the response has been patches, not replacement. Each patch plausible on its own terms, but accumulating in a way that looks, from the outside, less like a theory being refined and more like a theory being propped up. And I think about Ptolemy again, the geocentric model of the solar system. It was not wrong in a simple, easily detected way. It worked. It predicted the positions of the planets with reasonable accuracy. When the predictions drifted, you added an epicycle, a small circular orbit on top of the main circular orbit. Each epicycle improved the fit, and for centuries the model survived not because it was correct, but because the epicycles were good enough and the institutional investment in the geocentric worldview was too deep to challenge casually. It took Copernicus, Kepler, and Galileo, centuries of accumulated evidence, and several ruined careers to replace it. I am not saying Lambda CDM is Ptolemy's model. I am saying that the pattern of adding auxiliary hypotheses to protect a central theory from disconfirming data has a long and well-documented history in science. And the question of when adjustments become epicycles, when a theory is being refined versus when it is being propped up, is never obvious from the inside. It is only clear in retrospect. This is the lens through which I think the JWST data should be viewed, not as a single crisis to be resolved by a clever fix, but as a 23-year-long signal, getting louder with every observation, telling us that the early universe did something our models cannot accommodate without increasingly desperate modifications. The individual fixes are each plausible, the pattern of needing fix after fix after fix, each addressing a different aspect of the same underlying discrepancy, each going in the same direction. That pattern is the data. Williams put it simply: scientific discovery requires risk. The risk he took revealed that the cosmos is fuller than anyone imagined. The risk that JWST is now forcing us to take is larger. It is the risk of admitting that our model of the universe, the framework that has governed cosmological thinking for a generation, may need not adjustment, but replacement. And the data so far suggests that whatever replaces it will describe a universe that is stranger, more violent, more efficient, and more mysterious than anything we have yet imagined. Every time we look deeper, the universe is less like the universe we thought it was. I want to come back to Williams one final time, not because his story has a neat ending, but because it does not, and that is the point. In 2026, Robert Williams is 85 years old. He is still listed as an emeritus astronomer, at the Space Telescope Science Institute, the institution where he risked his career on a grain of sand 3 decades ago. The telescope he used to take the original deep field is still operating. 36 years after launch, its gyroscopes failing one by one, its instruments degrading but still collecting data, still contributing to the same surveys that JWST is now pushing to unprecedented depths. Williams lived long enough to see his gamble vindicated, not once, but repeatedly. Each deeper observation confirming that his instinct was correct, that the emptiest parts of the sky were not empty, that the darkness between the stars was full of things nobody had imagined. He also lived long enough to see what those things mean for the framework he spent his career working within. I do not know what Williams thinks about the JWST crisis. I have not seen a public statement from him about the universe breakers, or the little red dots, or the Hubble tension, but I imagine that if you asked him, the man who threatened to resign because his institution would not let him look at nothing, the man who gave discretionary time to the supernova teams that discovered dark energy, the man who spent his career taking risks that the system around him was too cautious to take, I imagine he would not be surprised that the cosmos turned out to be stranger than the models predicted. He pointed a telescope at the darkest, emptiest patch of sky he could find and discovered 3,000 galaxies. The universe rewarded his willingness to look where nobody else wanted to look. It has been rewarding that willingness ever since. The problem is that what it is showing us is not what we were prepared to see. There is something about the deep field observations that I keep returning to, a detail that feels almost metaphorical, but is actually just physics. The original Hubble Deep Field covered 1/24 millionth of the sky. The Ultra Deep Field covered 1/26 millionth. The Extreme Deep Field covered roughly 1/30 millionth. The JWST deep fields are similar in angular size. We have been staring at tiny, tiny fractions of the visible heavens. And in every one of those fractions, without exception, we have found more than we expected. The universe has been consistent. It has not hidden its surprises in one direction or one patch or one redshift range. Wherever we look, the early universe is more crowded, more luminous, more massive, more chemically enriched, and more structurally complex than the models say it should be. That consistency is itself a datum. It means the problem is not a local fluctuation or a statistical fluke or a calibration artifact. It is a property of the universe. The universe built itself faster than we thought possible. Period. Everywhere. Always. And we have barely started looking. The deep fields, for all their depth, cover a vanishingly small fraction of the sky. The total area surveyed to JWST depth is measured in arc minutes, and the full sky is 41,253 square degrees. We have examined a sliver, a flake of paint, off a cathedral ceiling. And already, the data is telling us that the building is not the building we mapped. Consider what is coming. The Cosmos Web Survey, the largest contiguous JWST imaging program in Cycle 1, covers an area more than 100 times larger than the original JWST deep field. It is mapping half a square degree of sky in 4 infrared bands, targeting the redshift range from 0.5 to 10, specifically designed to study the assembly of galaxies and the emergence of large-scale structure. When its data is fully analyzed, it will provide the first statistically robust census of galaxy populations at high redshift across a large enough area to capture the full range of cosmic environments, from voids to filaments to protoclusters. If the impossible galaxies are everywhere, Cosmos Web will confirm it beyond any statistical doubt. If they are only found in certain environments, Cosmos Web will show that too. And the environmental dependence itself would be a clue about what went wrong with the models. Then there is Euclid, the European Space Agency's Wide Field Space Telescope, launched in July of 2023. Euclid is designed to survey 15,000 square degrees of sky, roughly a third of the total, mapping the distribution of galaxies and dark matter out to a redshift of 2, using weak gravitational lensing and galaxy clustering. Its data, combined with JWST's depth, will create a three-dimensional map of cosmic structure from the nearby universe out to 10 billion years ago. And if Lambda CDM's predictions about the growth of structure are wrong, Euclid will show it, not in a pencil beam deep field, but across a third of the visible sky. And then there is the Vera C. Rubin Observatory in Chile, scheduled to begin its 10-year legacy survey of space and time in 2025. Rubin will photograph the entire southern sky every 3 nights, building up the deepest wide-field optical survey ever conducted, cataloging approximately 20 billion galaxies and 17 billion stars. It will measure the expansion history of the universe through Type Ia supernovae with a statistical sample thousands of times larger than anything currently available. If the Hubble tension is real, Rubin will confirm it with overwhelming statistical power. If dark energy is varying with time, as the early DSE hints suggest, Rubin will characterize that variation with precision that Lambda CDM cannot survive. The data pipeline is about to become a flood. JWST is still in its early years. Its instruments are performing above specification. Its fuel supply is sufficient for at least 20 years of operation. The surveys are ongoing. The proposals are stacking up. Every cycle brings deeper observations, wider fields, more spectra, more confirmations, more objects that should not exist. And each of those instruments, JWST, Euclid, Rubin, DESI, ALMA, they are all pointing at the same universe. Whatever that universe actually did in its first billion years, whatever the real physics of cosmic dawn looks like, it will not remain hidden for much longer. The question is not whether the truth will emerge. It is whether the community will be ready to accept it when it does, or whether the institutional inertia, the career investments, the psychological difficulty of abandoning a framework you have spent your professional life defending will delay the reckoning by years or decades. History suggests the delay is real. The data suggests the delay is costly. If the pattern holds, if every new instrument that looks at the early universe continues to find more than the models predicted, then we are not approaching a resolution. We are approaching a reckoning. And the reckoning will not be comfortable. It will not confirm the story you were told about the universe. It will replace it with something stranger, something less complete, something that honest physicists will have to describe with the most uncomfortable phrase in all of science: we do not know. And this is where I have to be honest about the limits of what I can tell you. I do not know what the right model of the universe looks like. Nobody does. That is the truthful answer, and I think it deserves to be spoken aloud more often than it is. The data from 23 years of staring at one patch of sky and then another, and then another, each time with a more powerful instrument, has told us, with increasing clarity and increasing statistical confidence, that the story we have been telling ourselves about how the universe assembled itself in its first billion years is not correct. The first galaxies were not small. They were not dim. They were not slow. They were enormous, luminous, chemically complex structures that appeared in the cosmic darkness hundreds of millions of years before our models say they should have been possible. And the objects alongside them, the overmassive black holes, the little red dots, the impossible galaxies, are not exceptions. They are the rule. The early universe was a factory running at an output level that our physics says is above the factory's maximum capacity. And yet, the products are there, real, measured, confirmed. The most common response to this, in the popular science press and in public lectures, is reassurance. We will figure it out. The models will be adjusted. New physics may be needed, but it will be found. Science is self-correcting. This is how it works. And there is truth in that. Science does self-correct, eventually. But the process of correction is not smooth, not automatic, and not without cost. It took decades for the Copernican model to replace Ptolemy. It took years for continental drift to be accepted. After Wegener first proposed it, it took a generation for quantum mechanics to overcome the resistance of physicists who could not accept its implications. And in every case, the delay was not caused by a lack of data. The data was there. The delay was caused by institutional inertia, by the human reluctance to abandon a framework that had served well for a long time, by the career structures and funding mechanisms and peer review norms that favor incremental refinement over revolutionary replacement. We are, I believe, in one of those moments now. The data is there. It has been there, accumulating for 23 years. And the response has been adjustment, not replacement. Patches, not reconstruction. That may be the right approach. It may be that one of the proposed fixes, or some combination of them, will eventually account for all the data within a modified Lambda CDM framework. But 23 years of trendline going in the same direction, with the discrepancy growing larger with each new dataset, is a long time to wait for the adjustments to converge. Jade's GS Zone 4, 0, is still out there, 13.5 billion light-years away, shining with the light of 500 million stars, burning with the oxygen forged inside stars that lived and died before our models say the first star should have been possible. It does not need our theories to explain it. It does not need our permission to exist. It has been there since before the Earth, before the Sun, before the Milky Way was fully assembled. And for 23 years, from the first Hubble Deep Field to the latest JWST spectroscopic confirmation, it and the objects like it have been saying the same thing. Quietly, consistently, with the patience of something that has been waiting 13 billion years to be noticed. You were not listening. Nobody was. And now the data is too clear, too deep, and too consistent to ignore. The calculations have been checked. The redshifts have been confirmed. The spectra have been measured. And the universe that built itself in the dark, before any telescope existed to watch, did something that our best mathematics says should not have been possible. It did it everywhere, behind every grain of sand you could hold at arm's length, in every direction, at every depth. The impossible is not an anomaly. It is the default state of the early cosmos, and we are only beginning to understand that we do not understand it at all.